So this is a collaborative effort between lots of people. So my colleagues, Mariona Claret and Eric Kunze at Northwest Research Associates in Seattle, and also Craig Winters at Scripps, who is responsible for the development of the code. And so that's why I put his name kind of in the center of this collaborator list. And what I'm going to present kind of grew out of a visit that Craig, Mariona, and I did to Sorbonne Université, to l'Océan, a visit hosted by Pascale Lelong and Yanis Pipert in 2023. So what we were interested in was to understand really how wind-driven energy exits the mixed layer and how it does that, and specifically with respect to anticyclones. So I'm using this nice picture from Jen McKinnon et al. Review paper. And so for purposes of this talk, I'm really interested in the processes, the generation processes of inertial gravity waves by the wind. Okay, so we're not going to worry about tides in this talk. And so we know that the wind excites primarily near-inertial motions, and because the mixed layer acts as a slab, these near-inertial motions are pretty much uniform in the mixed layer. We know also that the wind excites, a broad range of scales, but primarily very long horizontal scale near-inertial waves. We also know that most of that near-inertial energy is dissipated at the base of the mixed layer, but some we know escapes. And so how does it escape? So a number of processes have been suggested, but first I'll just give you just a little background refresher on frequencies of inertial gravity waves. So n here is the buoyancy frequency, which is a measure of stratification, and f is the Coriolis parameter. So in order to so the frequencies, constant frequencies, lie on these cones, and the group velocity associated with a particular wave number is perpendicular to this cone. So it's d omega dkh and d omega dm. And so in order to have vertical propagation, we have to have this term non-zero. And so you see that if kh is zero, then there's no vertical propagation. And so near-inertial motions having a very large length scale, horizontal length scale, means that their propagation on their own is quite small. And so here I've given you typical vertical group velocities for waves alone, just waves alone. And so it's typically 5 to 20 meters a day. And it takes 25 to 100 days to reach 500 meters. And it can take much, much longer to get down to 1,000 meters. So as we see, these inertial gravity waves, they propagate to depth on their own very, very slowly. So many mechanisms, or several mechanisms, I should say, have been proposed, and all of them really involve a shrinking of the horizontal wavelength so that these waves can propagate more efficiently. Just to give you a little background, so the term effective Coriolis frequency, which describes how background currents and shear can modify the propagation of these waves and the trapping and refraction effects. This was first introduced back in 1975. And so Moores introduced this concept of an effective Coriolis frequency. And later, when Eric Kunze was a graduate student, he did a very nice paper using ray tracing methods. And he derived the Doppler shifted dispersion relation for these inertial gravity waves in the presence of vertical shear and geotropic vorticity. And he found that the effective vorticity is reduced in regions where zeta, the vorticity, vertical vorticity, is negative. Okay, so this just expands the inertial gravity wave band. And so Eric Desaro predicted the amplitude and decay of near-inertial waves and found that in storms, these near-inertial waves actually decay on timescales of days in the mixed layer. And there's been lots of further theory, and I'm not going to go into it, but basically, when you have no eddies, the propagation downward is very slow. And when you do have anticyclonic trapping or focusing, which effectively reduces the frequency, the allowed frequencies that can propagate, you get much greater cruise velocities from 30 to 150 meters, so significant. And it can only take a week to get down to 1,000 meters, so a week to a month. And subsequently, or actually at the same time for Eric Quincy, there were lots of observations of waves trapped inside anticyclones, confirming Eric's theory. And I'll just mention, Eric's papers, because when I was asking him for references, he gave me these 3 references. So, but then I should also mention the boom experiment that kind of motivated some of my interest in this by Yannis Kripails and Pascale Lelong and others. And I'll mention more recent work by Ronan, who's here, who'll be talking this afternoon. So he has 2 nice papers on this topic as well. So, and then pretty much every time I look for references, there are more of these observations. So I'll just apologize to anybody who's not mentioned and say there are many, many different. All right. So motivated by the boom campaign, Yannis and Pascale's work, we did a nice little experiment where we just had a single eddy and geotropic, cyclogeotropic filaments actually, and looked at the propagation of wind-driven impulses at the inertial frequency as a function of depth. And I'm not going to go into this, but basically what we found was that the waves that we see at the bottom draw their energy entirely from the inertial oscillations. So here you see the inertial oscillations losing energy, and the waves gaining a little bit up here, and then mostly just accumulating at the bottom. And basically what happens is that the waves propagate down, and then at some point the eddy bottoms out, and the effective frequency, the effective Coriolis frequency goes back to what it was, and so these waves become trapped because while they benefited from the impact of the anticyclonic vorticity, once it's gone, they can no longer propagate, and so the energy accumulates. So this was the motivation for what I'm going to present next, which is, well, one of the things that we saw also is that this is an inherently multi-scale process. And so we've been doing Boussin-esque non-hydrostatic simulations, which are well suited to study, say, a simple eddy, one eddy. It's effective, also just perfect for modeling internal waves and turbulence, but it's often pseudospectral, at least ours is completely pseudospectral. And so the boundary conditions have to be simple, periodic or Riemann or Dirichlet. And the advantage is that They rely on few parameterizations, namely hyperviscosity, hyperdiffusion, but nothing else. But as I said, the inclusion of larger scales is quite limited to very simple features. So on the other hand, we could use an OGCM such as NEMO, which is hydrostatic. It's really well suited for modeling geostrophic flows, larger scale flows. It has all kinds of realistic boundaries, open boundaries. It's got bathymetry, it's got coastlines. It relies on quite a few parameterizations for unresolved physics because it just can't get down to small scales. And yeah, and one big problem for us is that the wind-driven near-inertial energy is well captured by these OGCMs, but there's just insufficient resolution at depth to see exactly what happens once the energy leaves the mixed layer. And so what we decided to do was to nest a Lucent model inside an OGCM. And one of the questions, of course, with these nested methods is, are the large-scale dynamics actually represented in smaller nested domains? How well does the dynamical signature of large scales come down? So this is a novel numerical technique that Craig devised, and we have a paper in James in 2024. So I'll just say that the approach really overcomes the limitations of OGCMs and of our Lucent model, because as I will show you, yeah. So actually, what we do, what we do for every variable in our domain, well, U, V, W, rho, etc. We expand all variables as the sum of this term f sub q, which is it's a cosine series, plus some Bernoulli polynomials, which have very nice recursion relations. So you can relate the nth Bernoulli polynomial to the n+1 through just this multiplication. And like Fourier modes, the derivatives of these Bernoulli polynomials just reduce to a multiplication. And so f sub q is actually just the okay, so what we do, we take our domain, and so we can have discontinuous derivatives, we can have non-periodic boundary conditions, we can have any kind of boundary conditions. And so we impose that these, okay, yeah, okay. So here is the Bernoulli polynomial at one end, at this end, and here's the Bernoulli polynomial extension at the other end. And so in one case, so for S0, we make the low order Bernoulli polynomials match the value of a function at 0, and it must have 0 derivatives at the other end. And then we apply the opposite condition at the other end of our domain. Okay, so we match the solution here, and we impose 0 derivatives from S sub L. Okay, and so yeah, the reason that f sub q can be expanded in cosine series is that if you take your full function and subtract these Bernoulli polynomial extensions, you end up with something with 0 derivatives and 0 values of the function at both ends. Okay. So we expand all of our variables in this fashion. So that's pretty much all I'm going to say about the method. If you're interested, we have the James paper, which details it in great detail. So, so we were focusing on the Mediterranean for a number of reasons. First of all, there are very high resolution simulations with NEMO of the Mediterranean basin. And the other good thing about the Mediterranean is that pretty much any dynamical phenomenon that you observe in larger domains, larger basins, is replicated in the Mediterranean on a limited scale. So, for example, geostrophic eddies can have radii of 20 kilometers instead of 200 kilometers. So it's quite nice. So we've done a number of studies in the Mediterranean using NEMO as our top nest. So for this particular application, we focused on an area of the Mediterranean just east of the Sicily Strait of Sicily, off the coast of Libya. And there is a semi-permanent gyre called the Sidra Gyre, Sidra eddy. It pretty much just sits in the Gulf of Sidra. It kind of precesses around, but it really doesn't move around much. And the other good thing about that is that EWM and Julien Sommet had a really nice simulation for this area with NEMO. So, very high lateral resolution, 300 vertical levels, bi-hourly saves of all the fields. So let's go and yeah, basically a very nice data set. And so the questions that we wanted to answer with our simulations are, is the dissipation at the base of the eddy driven by large-scale water column or local instability dynamics? More importantly, I think we know the answer, but do our nested simulations actually capture the large scale in the smaller nests? And another motivating question, kind of spurred on by two studies, one by our study in 2010 and by Eric Kunze's paper in 2019, unifying the theory of all the spectra that are observed in the ocean, is does the transition from breaking waves to 3D isotropic turbulence include a stratified turbulence intermediate phase? We don't know that. So can we answer this? So we did 4 levels of nesting. So here's the NEMO data set. And you see that we've got a big anticyclone here, you've got a smaller one over here, smaller eddy, you've got lots of things. Actually, the buoyancy period profile, actually, it's buoyancy frequency here. The NEMO data goes all the way down to 600 meters. And so to do our nesting, first of all, we need to stay away from coastlines, and we don't want to have bathymetry. We have a box. And so here is the first level of nesting. So we've taken a box, kind of oriented it parallel to the coast of Libya. And for this particular one, we went, so NEMO had a horizontal resolution of 1.5 kilometers and 1 to 50 meters in the vertical. One thing I should say is that for all of our nests, the vertical resolution is the same. It's 1 meter. Okay. So for this first parent one, we went down by a factor of 2 in horizontal scales. And we ran it for 17 days. July 20th, 2009 to 17 days later. So you can see, actually, one thing that you can see is that even with the parent simulation, we're capturing a lot more of the fine scale that was not present in Nemo. So the buoyancy frequency profile actually for the parent run goes all the way down to 500 meters like this. So here's the next level of nesting, which we call the trials. So here's and so what we do is basically force our models through the boundaries. We can handle time varying, non-periodic boundaries. And so we just do this, run the simulation. And again, more structure appears. And the large scales are coming through nicely.
In the beginning or the end?
This is, it's not the beginning. It's somewhere in between.
Crazy after some time? Or?
Probably, well, probably because as you can see, oops. Yeah. The first one we ran for 17 days. The next one we ran for 11, close to 12 days. Then 2.5 days. And then just a few hours. So when things start getting really wonky and we stop the simulation. Yeah. Okay, so there's the child. The grandchild now. Now we're down to horizontal resolutions of 43 meters and still 1 meter in the vertical. Okay, but our time step is now 1.25 seconds. So that's the other thing that we can't run indefinitely with those time steps. Okay, so more and more structure appears. And finally, the great grandchild is that little dot. And so every time what we do is that we shrink the vertical domain. And it's always centered on the eddy in the vertical. Okay. And for the last two nestings, we actually have a grid following the eddy core, so that we're always following the core. Yeah. So here's just a nice little schematic. The evolution, and then this doesn't show the gradient. And in the vertical, you can see the structure just increasing. So that's the parent, child. Oh, that's Nemo probably. Yeah, that's Nemo. That's the parent. So lots more structure. The child and the grandchild. And so in the grandchild simulation, what we find is that we actually have Richardson numbers that drop below a quarter. But the spatial, our grid scale in the horizontal is such that we actually can't have overturning. We can't have KH instability because the horizontal resolution is not sufficient. So when we go to the great grandchild, now our vertical domain is just 96 meters. And we're down to 1.5 kilometers in X or in Y and less, I can't remember, in X, but we retain dx equals dy in all these simulations. Okay, and so here's the grandchild domain, here's our great grandchild domain. So it encompasses the bottom of the eddy. Right. on a very linear scale. So kind of have to explain this picture because, okay, so we're moving, our grid is moving, and as it moves, it encounters now fluid from the grandchild simulation that is coarser. So all the small scales are missing. On the other hand, in the grandchild simulation, we do have bands of shear, very strong shear. We do have Richardson number dropping less to below a quarter. And so, I don't know if you can see this, it's very small. These are spectra averaged over different times. So it takes about four buoyancy periods for the turbulence to develop. But very quickly, so I don't know if you can see this, but the dark line is the horizontal spectrum of the horizontal kinetic energy. The light colored line is the vertical spectrum, actually twice the vertical spectrum, because our horizontal kinetic energy includes both U and V components. And so to get them on the same scale, we just multiply twice vertical one. And so you can see actually the development over time of this K to the minus 5/3 spectrum in both U, V, and W. Okay, the Ozmidov scale is indicated by this dashed line. The red regions indicate where we think we see 3D isotropic turbulence. And the gray area is where hyperviscosity is acting. And so in the very turbulent phase, we get this nice K to the minus 5/3. And here are movies showing what is happening in the great-grandchild simulation as a function of time. And so we see nice K. So that remember that the grid is moving into this region, into the forcing region that doesn't include small scales. So now let me just talk briefly about the vertical energy flux divergence. How well do our models actually flux energy down, and is it consistent? So you see here, so I've got the parent one, and these are from moorings, numerical moorings, obviously. Parent, child, grandchild, and great-grandchild. We see that the vertical energy flux divergence is pretty comparable across child, grandchild, and great-grandchild. The great-grandchild, you see this very positive flux divergence, indicating that it's a very strong sink. Okay, here you've got all kinds of things going on. Again, this is just from a mooring. If we look at horizontal domain averaged values, you see that the parent is actually supplying this negative sign indicates that this is a source of energy. And you see the characteristic sink right at the bottom. And for the child, again, horizontal domain averaged. So all the little fluctuations that we saw here are smoothed out. So what are we seeing? Can spectra help us to decide what we're seeing? So for internal waves, we know that, for example, the horizontal wave number spectrum often exhibits this k to the -2. Near-inertial waves dominated again, 10 to the -2 or flat. Stratified rotating turbulence in the horizontal, -5/3 extends. And strongly layered pancake turbulence, -5/3 to -3. And then isotropic turbulence, -5/3. Okay. For the vertical, we know that for stratified rotating turbulence, we're not going to have a -5/3 one. It's going to be much steeper. Yeah. Well, actually, sure. We see. So this is the Ozmidov scale represented here. And so what we see in the horizontal over this range of scales is a very definite -5/3 extending in the horizontal to here. This is for the grandchild run. For the child run, we see a transition to -2, which is characteristic of waves. And inertial, near-inertial waves have much less vertical kinetic energy. But I don't think I actually really understand these vertical energy spectra. Anyway, are we seeing stratified turbulence at this point? Last year I said yes. This year I'm saying probably not. Just looking at other things. The vertical energy spectra, again, for internal waves, often known as -2. For strongly layered pancake turbulence, -3 is a tendency. Stratified rotating turbulence, in between, and then isotropic turbulence, again, same thing, -5. So here are the vertical spectra that we get for different runs. So in the child run, we definitely have kz to the -2, so indicative of waves. The grandchild one, at the largest scales, behaves like waves. Then k to the -3 pretty strongly through here, indicating that there's a suppression of small vertical scales, which could be indicative of stratified turbulence. And down here, possibly k to the -5/3. In the great grandchild one, it's definitely k to the -5/3. So that's indicative of 3D turbulence. So on the other hand, if you look at the horizontal velocity versus depth, you see in the grandchild a very nearly circularly polarized signal, which means near-inertial waves. And on top of this very large signal, you see a lot of small-scale motions. Frequency spectra. The nice thing about this one is that it collapses to something isotropic at large frequencies, and at lower frequencies, there's definitely more energy in the low frequency motions, in the horizontal motions and in the vertical. I'll stop here and say I think we've successfully nested multiple nests, and we've spanned scales of order 100 kilometers to 1 meter, and we've captured, I believe, the outer scales of 3D isotropic turbulence. The impact of the large scales, I think, is successfully carried out through our sequence of nestings. So the wind-driven energy actually feeds the inertial gravity wave continuum, and through the vertical flux divergence terms, we see that this feeds the instabilities down to turbulent scales. I think the jury is still out on the stratigraphic turbulence regime question. So with this, thank you.